So this is the first of a series of a number of papers, and this is all to do with the new GCSE grade 9 to 1 papers. And this is the first of a specimen paper, and you can see that here. And it's the first of set 1. Now, what I'm going to try and do here is do the whole series of papers, and I'm starting with the foundation ones and working upwards to the higher. Previously on some of my videos for the old specification, I've done 8 higher GCSE papers for the old specification. Those 2 will be very useful for you, but if you're a year 10 student at the moment, then these papers are really for you because they are designed very well by Edexcel, in my opinion, to try and prepare you for the new specification. And what I'm going to try and do is work through the papers and help you through the questions. Okay, so by next year, next June, you'll be more than able to do well in your foundation and or higher GCSE paper. So that's the front page sorted here, and you can just read that at your leisure. I'm going to go through all the questions in the paper. If there are certain areas you're not quite sure on, I'm going to try and put some links to other videos that I have that explain things in a little bit more detail, like some of the topic areas, such as trigonometry, for example. So you can just go through the questions. I'm going to try and put a little grid of questions down the side, so you can just click on one of the questions and it will take you straight to the actual part in the video for that particular question. And that's going to take me quite a while to get those links sorted, but I'll try and do that for this paper, and then we'll just see how it goes. So good luck through the paper, and if you understand one of the questions very quickly, then just click to the next one. You don't have to watch all of it. Question 1 asks us to change 530 centimetres into metres. Well, if we look at the word centimetres here, this part means 1/100th of. So think about 1/100th of a metre, then you've got the idea of what a centimetre is. So if you think 1/100th of a metre is a centimetre, 1 centimetre, then what would 530 centimetres be? Well, if 100 centimetres gives you 1 metre, then 200 would be 2 metres, and so on, up to say 500 centimetres, that would give you 5 metres. Now, this is where it gets a bit tricky. So this is where some students find this quite difficult, and I can completely understand. What do you think 550 centimetres would be? Well, if 600 centimetres is 6 metres, then 550 centimetres would be 5.5 metres. So you're probably on the right tracks now to think what 530 would be, and the answer would be 530 centimetres would be 5.3 metres. Question 2. How many minutes are there in 3/4 of an hour? Well, in 1 hour there are 60 minutes. In half an hour there's 30 minutes. So think about it, 1/4 of an hour. Well, that will be 15 minutes. So if you know that 1 hour from here is 60 minutes, then 2 hours would be 120 minutes. And if you have another hour here, which you know is 60 minutes, then you can work out what 3 would be. Because if you add 2 and 1 together, you get the 3. So if you add the 120 and the 60 together, you get 180 minutes. So all you have to do now is add the 15 to the 180, and that gives you 195 minutes. And that would be 3¼ hours. Question 3. Write 4.4354 correct to 2 decimal places. Well, let's write that number out. So 4.4354, and we want to write it to 2 decimal places. Well, this is not a decimal place here. This is the first significant figure, so this is the units. If we see the decimal point here, the first number after the decimal point is the first decimal place. This number would be the second decimal place, and so on. So what you're asked to do is, you're really asked to round this number to 2 decimal places. So you've kind of like got a cut-off point here, say there, and you can either say that the answer's 4.43, so a lot of people would write that, but unfortunately that would not be the case. Now, for those that do have an idea about this or have seen it before but maybe can't remember, here's something you can look at. If you look at the next number, if that number is a 5, a 6, a 7, an 8 or a 9, then it has influence on the number it came after. I.e., in this case, this 5 would round this 3 to a 4. If, however, this number here was a 4, a 3, a 2, a 1 or a 0, then it would have no effect on the number it came after. So if this number, for example, was a 2, then you could simply write the answer 4.43, and that would be the answer. But let's look at this number again. It's a 5, so it is going to have influence on this number 3 and round it to a 4. So your answer would be 4.44, and I would always write 2dp here, because then I know that I've rounded it to 2 decimal places. Now, there are plenty more explanations as to why that rounding effect happens. I'm not going to go into that in this particular video, but there are videos out there, and I might do one myself one day, which explains rounding in a lot more detail. But I think for now, if you can just think about the number that comes after the number you want and use this key here, that would help. Question 4. Write 0.9 as a percentage. Well, a nice starting point here, if I was explaining this to someone, would be to say, what do you think 0.5 is? And a lot of people would agree, and hopefully you too, you would say, well, that's a half. And I would then say, well, if you got 1 out of 2 in a test, not a very big test, I agree, or you got half the marks, what percentage would that mean to you? And a lot of people would agree that it would be 50%. So 50% is quite well known to be a half or 0.5. Then I'd ask the question, and these are the kind of questions you must try and ask yourself when you revise, what would 0.6 be? Well, if 0.5 is 50%, then 0.6, it would make sense, would be 60%. And you could carry this up, this argument, and say 0.7, that would be 70%. And then you could quite easily understand then that 0.9 would indeed be 90%. Okay, so that's just a little explanation of how that question can work. There's many different ways of looking at percentages, but I think that's an easy way into the question that will help you understand why 0.9 is indeed 90%. Question 5, it says work out -3 to the power 3. Well, if we had something like a squared, then that would mean a multiplied by itself. It's like having a square of length a. You see, when you want to find the area, you multiply them together and you get an area of a squared. It's basically a square. In this case, you have a number -3 and you want to raise it to the power 3. But if we raise it to the power 2, what would we get? Well, we would have -3 multiplied by itself. Now, for some of you, you find it very difficult to understand why a negative multiplied by a negative is a positive. Well, let me try and do a quick explanation. If you took 3 times -2, well, 3 lots of a debt of 2 would be a debt of 6 altogether, so you'd get -6. 2 times -2 would be -4. 1 times -2 would be -2. No lots of -2, or 0 times -2 would just be 0. And I want you to look carefully at what we end up with here. So we've got -6, -4, -2, 0. And if you looked at that on a number line, where -6 is here, -4 is here, and so on, and there's 0, what do you think the next number here would be? Well, if you look at these numbers here, 3, 2, 1, 0, the next number here would be -1, and then in this column here we've kept -2 all the way down, so we'll keep that in there. Well, you should have understood and realised that these numbers are going up by 2 each time, so the next one would be 2. So -1 times -1 would indeed be 2. And that's one way of seeing that as soon as you have a negative times a negative, you end up with a positive, i.e. just 2. So that's one way of looking at it. But in the question that we have here, let's put that to one side, the question that we have is -3 times -3 times -3. Well, if we write that down as a sum like this, then it has a lot of similarities to 3 times 3 times 3. And we can work that out. That's 3 times 3 is 9, times 3 more is 27. But all we have to do in this situation is think, what is a negative times a negative? Well, from the previous example, we showed that that was a positive. So if this was a positive outcome, -3 times -3, which happens to be 9, then if we times it by a negative once more, wouldn't we be doing a positive here, this part here, times a negative, and that would give a negative. Just to remind you that when we looked at these numbers here, which you can just about see without me making a mistake, when we had a positive times a negative, we always got a negative. So one other way that I've done over the years is to just kind of like look at some numbers, and we'll look at that quickly here. If I just had -3 times -1 times 5 times -2, say, you can either look at the numbers first and just do 3 times 1, which is 3, times 5, which is 15, times 2, which is 30, and look at the signs afterwards. So you'd have a negative times a negative, which is a positive, and here you've got a positive times a negative, which is a negative, and then the final outcome will be a positive multiplied by a negative. And so the final answer would be negative 30. I'll do one more here. If we had negative 3 times negative 2 times negative 2 times negative 5. Let's do the signs first this time. Well, if we have a negative by a negative, that's positive, and then a negative by a negative, that's positive, and then look, we've got an outcome of a positive times a positive. Well, that's easy enough. The answer is going to be plus something. And don't forget, we wouldn't normally put the plus sign in front, would we? Okay, so now we can do the number part, and we'd have 3 times 2, which is 6, times 2, which is 12, times 5, which is 60. So the answer would be positive 60, or you could just write 60. Now I've just noticed in this part here, I probably said the answer was negative 27 overall. I can just check that again. A negative times a negative is positive, times a negative is a negative. So I should have written a negative there, and I'm sure some of you noticed that earlier on. So those kind of questions can be quite demanding, especially if you had a question like, say, negative 4 to the power 4. Well, if you think about it, that would be the same as just writing negative 4 multiplied by itself again, and then by itself one more time. So you could do the signs first. These two negatives make a positive. These two negatives make a positive. So the answer would be a positive answer. And then all you have to do is 4 times 4 times 4 times 4, which would actually be 256. And so you'll just write positive 256 or just 256. Okay, so that's a topic called directed numbers, or directed number. And it causes students and teachers quite a lot of difficulty. I'm not saying teachers can't do it, but it's quite difficult to explain to a class or an individual. So even I made a little error here and forgot to write the minus down here, so it's easy to make mistakes. Right, so that's that question done. Question 6. There's 4 cards and you have to write down the largest 4-digit even number. Well, if there's 4 digits, then this would represent the thousands column. This would be the hundreds, the tens and the units. So we would have to place the 5 here to make the more thousands as possible. So we want the answer to be 5,000 and something. Then we'd have to put the 4 here next because we'd want 400 at least. That would be the most hundreds we could make. But if you put the 2 here, that would leave the 1, which would make it an odd number because it would end in a 1, or an odd number. So what we'd have to do is we'd have to put the 1 here for the tens and then the 2 for the units. So the answer would be 5,412. Now in part B, we have to write down all the 2-digit numbers that can be made using these cards. So why don't we do it in a systematic way? So if we start with, I'll write these down again, 4, 5, 2 and 1. Why don't we start with all the ones starting in 4? So we could have 4 with the 5, 4 with the 2 and 4 with the 1. Then we could have, starting with the 5, we could have 5 with the 4, 5 with the 2 and 5 with the 1. Then we could go to the 2, and I'll just change the colour here. We can go 2 with the 4, 2 with the 5, and 2 with the 1. And then we could go with, I'll just change the colour again. We could go with the 1 and say 1 with the 4, 1 with the 5, and 1 with the 2. So there seems to be 3, 6, 9, 12 possibilities. And another way of you can do this, if you are stuck, is to just label the numbers 4, 5, 2 and 1 down the side for your first choice, and then do 4, 5, 2 and 1 for your second choice, and then you could do all the combinations. And you know that 4, 4 would not be allowed, because once you choose a card then it's chosen, so you can't choose the card twice. Although it doesn't say that in the part B, it does say it only once here. 5, 5 would not be allowed, 2, 2 would not be allowed, and 1, 1 would not be allowed. So all the other choices here that you could fill in this grid would be possibilities that you would write just here. To be honest with you, if you did write 4, 4, 5, 5, 2, 2 and 1, 1, then I'm pretty much sure you wouldn't be Dr. Mark if you showed all your workings and if you showed that somehow the question wasn't clear enough in what it was asking. Don't forget, these are specimen papers, these are not final papers, okay? So there's the workings for 6 part B. For question 7, I thought I'd do the chart first and then talk through it with you. You have to draw a suitable diagram or chart for this information. Now, it has boys and girls here and the actual sports involved. I've done a little note here. I could have written these out in full, which I suggest you probably would do, or just do a little key down the side. So this is the gender, i.e. boys and girls, and the sports that were done. And all I've done is split it boy, girl, for each of the sports: hockey, tennis, football and golf. I've labelled that axis here. Then I've labelled this one frequency, and I've gone up in twos: 2, 4, 6, 8, 10, 12, 14. This would be 16 here, so 15 would be halfway. And then I've clearly just put in boys hockey 3, girls hockey 6, and so on for tennis, football and golf. So it's like a bar chart, but it's a comparative bar chart, and I'll write that word down for you: comparative bar chart, because then you can quickly see how boys and girls differ with hockey and tennis and so on. Okay, so I would probably use a ruler for this in the exam and maybe write these out a little bit more in full down the side. Okay, so that's question 7. Question 8. When you have a whole number that ends in 8, you always get a number that ends in 4. And you have to write down an example to show that this is wrong. Well, if you took the number 8 and you halved it, you would indeed get 4. If you took a number, say like 28, and you halved it, you would get 14. If you took 48 and you halved it, you would get 24. So it seems that whatever number you choose, if you halve it, it will end in 4. But if you look at the ones in between, say 18, and here, say 38, if you halve those numbers, half of 18 is 9, and half of 38 is 19. So you can find plenty of examples now to show why that statement is wrong. The second part of the question has a statement saying, because 7 and 17 are both prime numbers, then all numbers that end in 7 are prime numbers? Well, it would seem so from this list, wouldn't it? You start with the smallest number ending in a 7, i.e. the units would be 7, and then in the tens you'd have 17. But if you wrote down 27, for example, that's a number that ends in 7, and is that a prime number? Well, how can you make the number 27? You can do 27 times 1, you can do 1 times 27, but you can also do 9 times 3, and so on. And you can probably find some others yourself. So I'm afraid 27 is not a prime number. What would you think about 37? Would you say that was prime? 47? Well, if you've played darts before, I think you'd see that 57 would be a number that you may have got quite a lot on the dartboard. That's treble 19, i.e. 3 times 19. So 57 wouldn't be prime either. Okay, so because 7 and 17 are both primes doesn't mean that all numbers ending in 7 that are whole numbers are indeed prime. You can always find a situation where you can disprove the statement. So just because the first few might be difficult, especially in the first part of the question, you could have been unfortunate enough and kept going off in like a sequence like 68, 88, and you could have given up thinking it was actually true. Okay, but keep persevering and it will work out in the end. Question 9. Work out 247 times 63. Well, one way that I do this is to do a grid. Right, 2, 4 and 7 here, 6 and 3, then do the times tables. So we'd have 6 times 2 is 12 and so on. So 24, 42, 6, 12 and 21. And then with this method, you start from the lower right hand corner here with 21, and the reason for that is because this would be the smallest type of number. This will be the units. How many units? These ones will be the tens, these ones will be the hundreds and thousands. And the reason for that is this 21 is made up of a unit, the 3, times the unit in the number 247, i.e. the 7. This number here is made up of a unit times a 10. So this is why it's a value of a 10. This 42 here means 42 tens, and the reason is because we have a 10 multiplied by a unit. So all you have to remember is to start from here and then go diagonally up the grid. Okay, and I've got plenty of videos on those multiplication rules and ways of doing it in other videos, and you can have a look at those at some other point. So if we have the number 21, we always put in the unit and carry everything else. The next two, how many tens would we have? Well, we'd have 12 of them and 42, which would make 54 tens, and then we'd have 2 more, so we'd have 56 tens altogether. So put in the unit here and carry everything else. 24 and 6, well, we're talking not units, not tens, but hundreds now, because we're in this hundreds column. So if we had 30 of them, you imagine putting this number down here, the unit part, and carrying everything else. So we'd have 6 and 24 is 30, and 5 more would be 35. So we put the 5 in here, carry everything else, and then 12 and the 3 would make 15. And we don't have to carry anything there. So the answer would be 15,561. Other methods that people have range from methods like this, or some people use grids where they put the 200s, the 40 and the 7, and then the 60 and the 3, and so on. and then they just add up the answers in the grid here. It's very similar, so if we took this one here, 60 by 40, we'd have 24 with 2 zeros, i.e. 2,400. But if you look here in this grid here, that 24 means 2400. And if we add it at the correct time, in order, we'd eventually add this value of 2,400 to what we needed. Okay, so the value I use, the method rather I use here is just a much quicker version of this one. But then again, it's a personal thing and it's up to you how you do your multiplication techniques. But there are plenty of videos out there, and I think I've got one video that has 5 or 6 different ways of doing it. Question 10. Now for a non-calculated paper, I think this question is very difficult. So what we'd have to try and do here is, because this suitcase shown on the diagram shows the maximum dimensions that can be used, they're all in inches. And we've got a conversion here that 1 inch is 2.54 centimetres. So Chris's bag, what we'd have to do is try and convert that into inches and see what it would be. So we have a height here of 50 centimetres. We have a width of his bag which is 40 centimetres. And there's a depth of 20 centimetres. So, finishing the diagram, that's what Chris's bag would be. Now we've got to see how that matches up. So, with this diagram here. So we're going to try and look at the height to start with. Now it says 1 inch is 2.54 centimetres. So if we look at the height here, we know it's 22 lots of 2.54, and that would be the conversion to centimetres. So we just need to do 22 times 254, and you can do that however you wish, but don't forget it's a non-calculator paper. So I'm going to do mine like so. So I've got 22 lots of 2, which is an estimate of around 44. So I'm going to have the answer as 55.88 centimetres going straight upwards. And he's only got 50, so that's okay for that height. Now we're going to look at, say, the depth, and that's 9 inches. So that would be 9 times 2.54 in centimetres. And again, I'll do 254 times 9. But I've got 2.54 times 10 roughly, which is about 20. So I'd have 22.86 centimetres. And the final dimension is 14 inches here on the width. So 14 lots of 254. Do your multiplication however you wish. And I've got videos on this way if you want to see them. So I've got 35.56, which is allowable, but look, his is 40 in terms of the width. So he kind of says, he breaks the criteria here, it's not allowed. So I would say that Chris could not take his bag on the plane because it's more than the width allowed. The depth is fine and the height was fine, but the width was too much on Chris's baggage, so I would say no, he couldn't take it on the plane. Question 11. You have to complete the two-way table. So in this situation, it's called a two-way table because we have things going down one column and then we have information going across. And it's got to make sense whichever way you read the table. So for example, in this instance we have a grand total of 12, but we're reading this way, and we already have a 5 and a 4 for blue eyes and green eyes, and so if 5 and 4 makes 9, we're missing a 3 here. And what that would mean is that if we wanted to look at the information for boys and what type of eye colour they had, we just add these numbers going horizontally, okay, and we'd get the total 12. But then if you look vertically, we've got a total of 30, and that would represent the totals for all boys and girls. Then we've got a 12 here, so surely we're missing an 18 here, because only 12 and 18 would make the 30. And then likewise, you just start looking and try and fill in all the gaps. So we've got a 4 and something makes 9, and that would be 5. Then we've got a 7 and a 5 makes 12, and something makes 18, so that something will be 6. And then these ones you just read down and put the totals in. So that this column would be boys and girls who have blue eyes, and that would be the total. So you can just add those, put 11, this one will be 10, we've got the 9 already, and then we can just double check. 11 and 9 is 20, and 10 makes 30. So looking at a two-way table, it's a personal choice again, but you just try and fill in the information that makes sense, and they'll always give you enough. It's not going to be a trick or a puzzle. It's basically common sense. Question 13, it shows you a sequence of patterns, and you have to try and work out pattern number 4. Well, you should be able to see that the grey grows by 1 each time. So for pattern number 3, there's 1, 2, 3, 4, 5. So for pattern number 4, there should be 6 of the grey. And if you look at the number of white here, they start from the centre and they build outwards, and they go up 1, 2, 3. So there's going to be 4 of those. So there you go, there's pattern number 4. Now it says find the total number of tiles in pattern number 20, and this is where you've got to start thinking strategically. Okay, so in pattern number 20, how many grey tiles do you think there'll be first? Well, in pattern number 3 you had 1, 2, 3, 4, 5. In pattern number 2 you had 1, 2, 3, 4, and in pattern number 1 you had 3. Can you see that it's always 2 more than the pattern number? That's how many grey tiles you'd have. So in pattern number 20 you would have 2 more than 20 grey tiles, so you'd have 22 grey. And then also, can you spot that the number of white tiles is exactly the same as the pattern number? So in pattern number 20 you would have 20 white. So the total number of tiles would be 22 and 20, which is 42 tiles. It then wants you to write an expression in terms of n for the number of grey tiles in pattern number n. Well, one way of looking at this, we can say the pattern number here versus how many grey tiles. So pattern number 1, 2, 3, 4, pattern number n, and then the grey tiles starts 3, 4, 5, 6, and so on. Can you still see that the pattern number is always 2 less than the number of grey tiles? So you can say that the number of grey tiles is always 2 more than the pattern number. So in this case we'd have the pattern number add 2, and that would be the expression for the number of grey tiles in pattern number N. Question 14. A unit of gas costs 4.2 pence. On average, Ria uses 50.1 units of gas a week. She pays for the gas she uses in 13 weeks. Work out an estimate for the amount Ria pays. Now, when doing estimates, it's always good to follow this rule. Try and use numbers that you can do very simply in your head. So, if she uses 4.2 pence for each unit, then let's just use that as, say, 4, because that's a nice rounded estimate. Then she uses 50 units, roughly. We don't have to say 50.1. 50 is a nice estimate for 50.1 of gas a week. And she pays for the gas she uses in 13 weeks. And there's nothing wrong with just using 13 there, because that's a nice rounded number anyway. You probably could have used 10 here, but 13 would be fine. So this is the pence, this is the units of gas used, and this is the weeks. So we'd have to multiply these together to get the total. So we can do this in a number of ways in our head. We can say 4 times 50 is 200, and then times that by the 13. We know that 2 13s are 26, but we had 200 lots of 13, so that will be 100 times bigger, which is 2,600 pence. And of course, if you wanted to make that in terms of pounds, which you don't have to in the exam, you'd get the 3 marks for writing that. You could say there's 100 pence for every pound, so you could just say 26 pounds if you really wanted. But 2,600 pence is absolutely fine also. For part B, it says, is your estimate to part A an underestimate or an overestimate? Give a reason for your answer. Well, the actual amount would have been 4.2 times 50.1 times 13. And what we did, we underestimated this. We underestimated this. And we left this one the same. So if we had underestimated these two, then surely our answer would have been an underestimate. And you would say, because we rounded down twice. If you'd have rounded up, say to 5, maybe left this one the same and rounded this one up to 15, then you would have had an overestimate for different reasons. Okay, so as long as you're clear on what you're doing, then as long as you write that down, you'll get the mark. Question 15. It says here this is a scale plan for a rectangular floor. The difficulty with this question and the fact that I'm using a computer is that I don't have a paper copy in front of me to measure. So the first thing that I'll do with this question is leave you to do some of the measurements yourself using a ruler and pencil. What I can say is that if 150 boards are used by Mr. Bridges, then we can at least say that we've got 150 times the dimensions of each board, and we can convert those into centimetres. So we can say 150 by 120 by 100. And these here were in centimetres and centimetres. So we had, let's have a look, 10, 100, 1,000, with 10 more. And we've got 15 by 1, which is 15 by 12. So we've got 15 times 12. And we can work that out. So we got 5, 6, 7, 8. So we have 1,800,000 centimetre squares, and that is the same as 180 metre squares, because 100 centimetres by 100 centimetres is the same as 1 metre by 1 metre, which is 1 metre squares. And if you do 100 centimetres times 100 centimetres, then that's these 4 zeros here, 4 powers of 10, leaving you the 180 metre squares. So looking at the mark scheme, it seems to me that if you were to measure this, and hopefully this is correct, and I can't tell because I'm on a computer here, that this should measure 4 centimetres by 12 centimetres if you were to use a ruler. And in that case, if 1 centimetre represents 2 metres, then this board, or this floor rather, in real life, you'd have to use 1 centimetre is 2 metres, while it would represent 8 metres by 24 metres. And in terms of area, that will be 8 by 24, which should be 192 metre squares. And as we've worked out previously, all 150 boards would only be 180 metre squares, and 180 is less than 192, which would be needed. So that would be one way of saying there is just not enough boards. Okay, so I'm sorry if I made that a little bit too complicated, but it is a non-calculator paper, and I guess what you could have done here is just had it all in metre squares to begin with. But at least you've learnt how to convert from centimetre squares to metre squares anyway. Okay, so try that with a paper in front of you and see if you agree with the way I've worked that out. Question 16, you've got to work out the area of the shape shown. So I'm just going to zoom in and we're going to try and work out the area of this shape. Well, a few things come to mind. I could split the shape up into 2 parts here, and I can label the lengths. So I know that this stays as 2, but because this was 8 and this is 2, then this must be 6. So the area of this part here will be 6 times 2, which is 12 centimetres by centimetres, 12 centimetre squares. Also, we know that this stays as 10, and this was 2 already, so the area of this part here is going to be 2 by 10, which is 20 centimetre squares. So the total area, looking at that way, would be 32 centimetre squares, because we just add the 20 and the 12 together. Now, there are other ways of doing this as well. I'm not going to go into these into too much depth, but if you had your L shape, like so, then you could have split it this way, or this way, to make 2 trapezia, but that would have been quite a lot more difficult. So basically a vertical or a horizontal split would have been the easiest way around this problem. Question 18. There are 500 passengers on a train, and you'll basically have to work out 7/20 of them and 40% of them. And the 7/20 would be men and the 40% would be women. So Once we've worked that out, there'd be some left over and they would be children, and you have to work out the number of children on the train. So let's start with what I think is the easiest one, and that is 40%. So if we want to work out 40% of 500, well, 100% of 500 is 500. 10% of 500 would be 10 times less, which is 50. 20% of 500 would be 100, because I just doubled this and doubled this. And that would mean that 40% of 500 would be double this again, which is 200. So there's 200, nearly made a mistake there, there's 200 women. Now, let's do 7/20ths of 500. Well, I hope you've noticed here that I've used of in this situation. Now, some of you may have been taught by your teacher that if you wanted to work 40% of 500 out, and I'll make a bit of room here. So if you wanted to do 40% of 500, then some teachers would show you this method where you could write 40% as a fraction. Of would be times 500. It's like saying I want 3 of these and they cost £2. So the sum would be 3 times 2. So of would be times. So think of as being times in mathematics. And then if you had a calculator or not, it's up to you. You could say, well, 100 into 500 is 5. And then you're left with 40 times 5, which is 200. On a calculator, if you did 40 divided by 100 times 500, you would get exactly the same answer. So in this case here, of is times again. So you'd have 7/20ths times 500. So if you had a calculator, and this paper is not a calculator paper, you would do 7 divided by 20 times 500, or 7 times 500 divided by 20 and get an answer. But as this is a non-calculator paper, we've got to try and find another way of looking at this. So one way is to say, and this is quite complicated if you don't know fractions very well, but if you make 500 into 500 whole ones, then because we're multiplying, it doesn't matter which order we write the numerators or the denominators. So I'll explain this a little bit more. If you take the 7/20ths and you switch these two denominators around, because it's under multiplication, that's the same as 7 whole ones times 500/20ths. It's exactly the same answer. Now, 7 whole ones cannot be cancelled down, but if you looked at this fraction here, 500 over 20, that's the same as 50 over 2, because I've divided top and bottom by 10. And 50 over 2, you should know, is the same as 25 over 1, or 25 whole ones. Just think of 50 over 2 as being 50 divided by 2. So what you'll be left with is 7 whole ones times 25 whole ones, and then you don't need to write this denominator here, so the answer would just be 7 times 25. And if you know that 4 25s is 100 and 3 25s is 75, then you've got the answer here, that there would be 175 men. So we can work out the number of children now, here, because if we know there's 175 men and 200 women, that's 375 men and women, so that would leave 125 children, because we knew there was 500 passengers on the train altogether. So I've gone in a bit more detail there, but for some of you this kind of question is very difficult. So for those that get it, then you can just skim through the questions. If you don't get it, then I suggest you watch the whole thing over again and try and learn from it. Now these type of questions definitely terrify a lot of students because there's so much to read, so much to work out, but I'm afraid they're on the paper. They're things that we have to look at. I guess there's quite a few things in life that are as complicated to work out in certain situations. So we've got to tackle these type of questions. So it's about milk, and it says first of all that Martin has none to start with, and we've got to assume that he uses on average 3/4 of a pint of milk each day. So he wants to buy enough to last for 7 days. So the first thing you've got to look at is what would 3/4 of a pint per day for 7 days be? Well, we can do this sum here, 3/4 of 7, or 3/4 times 7. And we can work that out as being 21/4, which is, now if you think 4's into 21, you can do by long division. 4's into the 2, 4's into the 21, 1 left over, and so on. Okay, so I'm not going to go into long division, but 21 divided by 4 is 5.25, or 5 1/4. So I'm going to say 5.25 pints, or thereabouts, needed. So the other thing to do is you've got to work out the smallest amount of money. So you've got to get a good deal. And basically, to get a good deal, you think that 1 pint here is 52, and the 2 pints are 93, which if you bought a 2-pint bottle would mean you'd only have to pay 46.5p to buy the 2 pints worth. If you bought too many of the 1-pinters, then you'd be spending too much money. So if we want 5.25 pints, then what I would do is this. I would say, well, I'd definitely have to get the 5, and I'd have to buy a little bit more because on average I'd have 5.25 pints. So I would do 3 lots of the 2-pint bottle. And that would mean I'd have to work out 3 times 93 in pence, and I would get 3 times the 3 and 3 times the 9, so I'd have 279. Okay, so I'm not going to go into too much how to do 93 times 3 right now, but you should be able to have a look at that. So in buying 3 of the 2 pints, then you've spent £2.79, and although you've got 6 pints, you've at least covered yourself for what you needed at least. If you'd done it any other way, you'd have spent more, and you can have a look at that later if you want. It says here now that Martin actually uses more than 3/4 of a pint of milk each day. And it says here, explain how this might affect the amount of money he needs to spend on milk. Now again, I find this a very difficult question for myself. So goodness knows how some of the students must feel about reading this. You've just got to make sense of it though. You had to clear 5.25 pints. And don't forget, in part A, you bought 6 pints because you bought 3 of the 2 pints. Okay? Now, that meant that you had 6 pints available. And if you imagined you were Martin here and you actually used more than 3/4 of a pint of milk each day, then I would say, as long as you didn't use more than 6 pints in the week, you would be okay. If you had a calculator, then I think you wouldn't be able to go over the 6 pints that you had available divided by the 7 days, and I think off the top of my head that's roughly 0.857 pints per day. So if you basically went over that, then you'd be in danger of running out. Okay, and then you'd have to spend more money. Okay, so let's move on now to another question. Question 20. There's a diagram of a right-angled triangle, and it says all the angles are in degrees. Work out the size of the smallest angle of the triangle. Well, we know that angles in a triangle add up to 180 degrees, so we know that 7x plus 5x plus 18 plus the 90 has to equal 180. In fact, what we could have said is that 7x plus 5x plus 18 would have to be 90, because don't forget this angle and this angle would have to make 90 because we already have a 90 given in our triangle. So all we have to do is simplify this left hand side and we get 12x plus 18 equals 90. If I take 18 from both sides of this equation, then I would have 12x equals 72. And think about this, 12 times what gives 72? Well, 6 12s are 72. So if we were to divide both sides by 12, then we would have x on its own is equal to 72 divided by 12, which is 6. So we know that from this diagram here, we know that x equals 6 degrees. And it says, though, we must work out the size of the smallest angle. So this angle here would be worth 7 sixes, which is 42 degrees. This angle here would be 5 times 6, which is 30, plus the 18, which is 48 degrees. And this angle here is obviously 90 degrees because it's already given. So the smallest angle of the triangle would in this case be 42 degrees. Okay? Question 21. A box exerts a force of 140 newtons on a table. The pressure on the table is 35 newtons per metre square. Calculate the area of the box that is in contact with the table. Now, that would frighten a lot of people, especially if you don't have a very good physics background, or indeed if you don't know what a newton is, for example. But the nice thing about this question is it does tell you that pressure equals force, which is in newtons, over area, which you will know is usually in metre squares. And if you have newtons per metre square, that just means you'll have newtons over metre squares at some point, which is exactly what you have here. So all you have to do is calculate the area, and it gives you these two parts. So we know that P is the pressure, which is 35. We know the force is 140, and we wish to work out the area. Now what you can do is, you don't have to use algebra necessarily to rearrange this for A. You can kind of use your common sense. If A was 2, say, you would have 140 divided by 2, which would give 70. But if you divided that by 2 again, then you would get 35. So 140 divided by 4 would be a very good idea. Therefore, the area would be 4 metre squares, because if you did 4s into 140, that is the same as 70 divided by 2, just halving this and halving this. And then 70 divided by 2 is the same as 35 divided by 1, by halving top and bottom again, which is what you can do when you have equivalent fractions. So that's the way of doing it in your head, and you could simply just write A is 4 metre squares, If you'd prefer something a little bit more algebraic, then what you can do is you can treat this as a fraction, 35 divided by 1. And what you can do is you can turn this fraction upside down by doing the reciprocal. So that's something to look up. The reciprocal. It's sometimes known as inverting the fraction, or inverting the left-hand side or right-hand side. And as long as you do exactly the same to this one, i.e. e to the power minus 1, then what you'd end up with is 1 divided by 35 is a divided by 140. And then what you could do is, to both sides, is you could times both sides by this denominator here of 140, and you would get 140 divided by 35 equals a, and then you would simply get a is 4. Another way of looking at this, if you're not happy with that, is that when you had your original question here, 35 equals 140 over a, instead of inverting both sides, i.e. doing the reciprocal, you could have just times both sides by capital A, and then you would have had 35 lots of capital A for the area would be 140, and then 35A means 35 times A, so if you divided both sides by 35 in this case, you would then have A equals 140 over 35, which is 4. If you can't see that's 4, then you might have to do things like factors. So say if you had 140 over 35, 140 is 7 times 20, 35 is 7 times 5. Here the 7's cancel, 7 divided by 7 is 1. But can you see that 20 divided by 5 is quite nice? You should be able to see that that is indeed 4. So there are plenty of ways of getting the answer of 4, but I do understand that for some students doing foundation, this can be quite a scary question. And I know I've had a few criticisms from people saying that I take too long in the explanations. Well, it's very simple. If you get the idea, then just move along to the next question. But I'm really trying to make sure that all the students that are doing this paper will have a good chance of success. Question 22. There are only red counters, blue counters and green counters and yellow counters in a bag. The table shows the probabilities of picking at random a red and a yellow counter. So they're filled in for us. We've got to work out the probability of picking a blue counter and a green counter, and it tells you that the probability of picking a blue is the same as the probability of picking a green. So the first thing that we've got to recognise is that the probability of picking one of these colours, at least, when you add them all up, will equal 1, i.e. it's certain that you'll choose one of the colours at least. So we know we already have 0.24 for red, and we have 0.32 for yellow. So if we add those up, you can see here we get 0.56. So you should be able to work out that there's 0.44 left, because only 0.44 and 0.56 will equal 1. So if we add these up, that will be certainty, i.e. 1 or 100%. So we know it's 0.44 between these two, and as it said the probability of picking them is the same, then we just halve 0.44 and we can put 0.22 in for each one, and it's as simple as that. So really we've just been tested to realise that all the chances for each of the colours would have to add to 1. Question 23. When I sat down with one of my students a few weeks ago looking at this question, I too felt this was quite difficult, and one way I came about explaining this was like so. I said, if you take this length here and call it x, and then this length here and call it y, would it not be true then that you'd have x plus y equals 7? Because that would be this entire length here. Then, if we looked at this length here, this also would be x, and so would this, and this here would be y. So would it be true to say that 2x plus y would be equal to 11? You see, x plus x, 2x, plus y would be 11. So we seem to get a pair of simultaneous equations. Now, that also fills some people with dread, this topic, simultaneous equations. Now, I'm not going to explain fully how to do these here, but they're very useful, especially in this type of context, and I think that's what the question is trying to get out of you. Can you somehow work out these values to help find the total area of the pattern? And I think that simultaneous equations is a very difficult topic, but I have got some good videos, as have other people on YouTube, and I'll try and put some links up for this question when I upload it. So don't worry too much. Let's try and carry on with the question and see how much you can understand. Well, if this equation is true and this equation is true, then what I can do is, say for the top equation, x plus y equals 7, I can times the left-hand side and the right-hand side by -1, and that would give me minus x minus y equals -7. And just keep that in mind for now. I'm not going to change this one. I'm going to keep that as 2x plus y equals 11. And then what I'm going to do is I'm going to add these elements together, i.e. the left-hand sides together, and then I'm going to add the right-hand sides together as well. And they should still balance, because if you think about it, if this was a pair of scales here, and that balanced, and this also was a pair of scales which were in complete balance, and why were they balancing? Because they had an equal sign here between them. Then if I had a quantity on here and a quantity here, here and here, that all balanced, I could put these two quantities together and make a new quantity on a new pair of scales, and as long as I did the same to the other, then left and right should still balance. And that's really in essence how to work out simultaneous equations. So let's have a look what we've got. We've got minus x and 2x, which will just give you x here. Minus y, add y, will cancel to give 0. Equals here. And then -7 and 11, or 11 and -7. Either way, the answer will be 4. So x will be 4. Well, that's easy now to find y, because we can just use this diagram here. If this is 4, then y has to be 3, because together they make 7. So y is 3. Now we can find the area of the pattern in total. Because if this measures 4 by 3, because this length here is going to be the same as this one here, then this is 12. They're all identical rectangular tiles, so this would be 12, this would be 12, and this would be 12. So the total area will be 4 12s, which is 48, and it will be in centimetre squares. So that's the way I explained it to one of my students. If you've got another way of explaining it, I'd really like to hear that, and you'd be most welcome to comment. Question 24. The diagram shows a sand pit, and it's in the shape of a cuboid. And you've got to work out whether it's going to cost more than £70 or less than £70. And then we have to test to see whether what Sally said is correct or not. So I think the first thing we should do is work out the total volume in litres of the cuboid. So we take a corner and we just look at the dimensions, okay, in all directions. So we've got 40 going up, we've got 100 for one of the base lengths, and we've got here 60 for the base width. So we've got like height, width and length. Doesn't really matter which way round you do these as long as you're multiplying each of the three together. So in this case we can see that we have 10, 100 and 1,000. So we have 1, 2, 3, 4 powers of 10. And then we just have the numbers 4 times 1 times 6. And 4 times 1 is 4 times 6 is 24. So we have 240,000 centimetre cubes of volume available for that sandpit. Now, we know there is 8 litres of sand in each bag, and in this case it's rather strange to use the word litre of sand. I would have probably said 8,000 centimetre cubes or something, because sand to me is not like a liquid, but you know, this is what the question says, so we'll work with it. 1 litre is 1,000 millilitres. So in this case we're looking at as the sand behaving like a liquid, and we've got 1,000 centimetre cubes. So that's 1 litre. So an 8 litre bag would have 8,000 centimetre cubes in it. So if we wanted to work out how many bags we'd have to buy, or Sally would have to buy, then we could do it like this. We can look at the total capacity. So I'll write that keyword down, capacity of the sandpit in centimetre cubes, and we can divide that by what one bag would be in centimetre cubes. And we can do some simple cancelling without a calculator. And 240 divided by 8 as a fraction would be 120 divided by 4, which would be 60 divided by 2, which is 30 bags. Now each of those bags cost £2.50. So 3 bags would be 3 lots of £2.50, which is £7.50. So 30 bags would be 10 times more than £7.50. So what do you think that would be? Well, if 3 times £2.50 is £7.50, then 30 bags would be £75. So when Sally says the sand will cost less than £70, Sally is wrong. And that's how I would attempt that question. Question 25, it says 4 friends each throw a biased, i.e. not fairly weighted coin, i.e. it's more likely to come down on one side than the other, a number of times. The table shows the number of heads and the number of tails each friend got. The first part of the question says, the coin is to be thrown one more time. Which of the 4 friends' results will give the best estimate for the probability that the coin will land heads? Well, when you're working out probability from experimental data, i.e. you've got people in a room and you give them a biased coin and they were to throw it a number of times, you would generally trust the person who threw it more times. This is because after many trials, so if I write this word down here, trials, the more trials you do, the more general your pattern becomes, i.e. it will settle down to some particular value the more you do the trials. So if you were to throw that coin maybe 1,000,000 times and worked out the probability from the ratio of heads to tails, then that would be a lot more trustworthy than maybe just doing it 5 or 6 times. Okay, so the more times you do something, the more reliable the data you have. So in this case, Sharif is the one who I would rely on the most. So I'd write that down, and all you need to do is say something like, because there were more trials involved with Sharif. Okay, or something of that nature. It's only 1 mark, so that's all you need to say. It's all about something called, and the topic is relative frequency. Okay, so you can look that up or talk with your teacher about that. The next part of the question says, Paul says, with this coin, you are twice as likely to get heads as to get tails. Is Paul correct? Well, in terms of Paul's data, he would think that, wouldn't he? Because he did get twice as many heads as there is tails. But don't forget, we're looking at having a reliable set of data, i.e. the more you flip that coin, the more reliable the data will be, because you'll start to see a pattern. Now Sharif threw the coin 160 times in total and got 120 out of 160 as heads. Now, if you think about it, was the number of heads twice as much as tails? Well, no, it wasn't. It was 3 times as much. So I would say, no, Paul is incorrect because he cannot base it on his data alone. Sharif's data indicates that his assertion, when I say assertion, he asserts or says this, that his assertion is incorrect. Now that's obviously how I would write it, but you can just say no, Sharif did it more times and this was not the trend that he got from his data. Anything of that nature will do. Now, the last part, it says the coin is to be thrown twice. Use all the results in the table, and this is key, all the results in the table, to work out an estimate for the probability that the coin will land on heads both times. So this is by far the most difficult 2 marks on this question. So what we'd have to look at is, if we want the first coin, so if we look at a probability tree, if we have our first coin here, and that is flipped or thrown, then it can either be head or it can be tails. Now, the probability based on all the data is if you'd have to add up all of these together. So that's the total number of trials by all 4 people. And if you added 120, 80, 66 and 34 together, you would get 300. And if you added the tails together, you would get 80 and 12 and 8 would be 100. So out of all the 400 trials, you would have 300 out of 400 being heads. So you would assert from this that the probability of getting a head would be 300 out of 400, which is the same as 3/4. So you would clearly say 3/4 based on your relative frequency for heads, which would mean 1/4 for tails. And then when you came to do it the second time, so when I say the second coin, I mean the coin is thrown twice, so the second occasion it's thrown, you would have exactly the same situation. You would have heads and tails here, and you would have 3/4 here and 1/4, 3/4 and 1/4. Now, I have done a video about explaining why you multiply these probabilities together, and I can put a link on here, and of course other people have these on YouTube as well. You don't have to depend on mine. So the probability of getting 2 heads would be 3/4 multiplied by 3/4, which would be 9/16, because you would just times the numerators together and the denominators together. Of course, if you'd have kept with this one, you could have said 300 400ths times 300 400ths, and you would have got 90,000 over 160,000, which would have been exactly the same as 9/16. Okay, so it doesn't matter which number you had used. So I hope you get a bit of an idea about relative frequency and how it can be really useful with probability. Question 26. Write down the exact value of cos 30 or cosine of 30. Well, the cosine of 30 is the same as the sine of 60, because these two angles here add up to 90. Now, in the new specification, foundation students have to know the sines, cosines and tangents of angles like 30, 60, 90 and 0 and so on, and 45. And I suggest that it's rather too difficult for me to explain this right here, right now on this particular paper, but I will add an annotation so you can click on the annotation and be taken to a video which will give a full explanation of how these are found. You don't have to look at my explanations. There are some other good explanations on YouTube that would help you in this matter. But it's a fact to say that if we want to look at the cosine of 30, then a quick explanation would be this. If you draw an equilateral triangle whose angles are all 60, and you call the lengths 2, for example, that if you drop down a perpendicular here, then in the left triangle or the right one, you would have a right angle here. This length would be 1 because it would be half of this 2 here. This length here would be 2. So by Pythagoras, this length here would be 2 squared minus 1 squared, which would be root 3. This angle remains as 60 because this hasn't changed. And then what you would have is, you would have the cosine of 60 using SOHCAHTOA. The cosine of 60 would be adjacent over hypotenuse. So the cosine of 60 would be a half. But if you wanted the cosine of 30, which is what the question asks, then you should understand that if you've halved this angle here, then this would be 30 degrees, because from here you had 60 but you wanted just half of it. So if you did the cosine of 30, then you would have adjacent over hypotenuse, which is root 3 over 2. So the answer would be root 3 over 2. Part B, there's a diagram of a right-angled triangle, and it says given that the sine of 30 is 0.5, work out the value of x. Well, for my previous diagram here, if I can find it, was if we looked at this triangle that we spoke about earlier, then the sine of 30 would be opposite over hypotenuse, which is a half, which is given. So that makes complete sense. And we've just got to work out the value of x. Well, let's have a look at the diagram. We have the opposite here, and we have the hypotenuse here. So using SOHCAHTOA, and again, I've said on many of my videos that SOHCAHTOA is absolutely fine as long as you understand where it comes from. And if your teacher hasn't explained that to you, where it comes from, then you just need to have a look around at a few other videos. I have plenty there which explain it from first principles. So sine of 30 is a half, and so the sine of 30 here would be opposite, which is x, over hypotenuse, which is 12. And then all you have to do is times both sides here by 12, and you would get 12 times sine 30 equals x. It tells you what the sine of 30 is, which is 0.5, so you just have 12 times 0.5 equals x. So of course x will be just 6 centimetres, and that would be your answer. Okay, so don't forget there's plenty of videos on the unit circle, so always look out for that topic keywords, and if you look at videos about the unit circle, all of this sine, cos and tan business will become very clear. Question 27, it says expand and simplify x plus 3 multiplied by x minus 1. And I think a good way here is to use the grid method here. And you fill in the missing parts by multiplication. So 3x here, minus x, and then minus 3. Because don't forget, we just want to multiply x by x here. X by 3 will give you 3 lots of x. 1 lot of x is just x, but we have minus 1 lots of x, i.e. a negative times a positive would be a negative, and then also 1 times 3 is 3, so negative 1 times positive 3 would be a negative 3. So all we have to do is now add these up, and we simply have x squared, 3x and negative x. Well, if I had £3 in the bank and I spent £1, then I would have £2 left. So think of this that way. So we have 2x here, and then we finally have the minus 3. So that would be your full answer to question 27. Question 28. Factorise x squared minus 16. Well, if I gave you something like this, 25 minus 4, well, you know the answer is 21. The thing about 25 and 4 is they're both square numbers. So I could write that as 5 squared minus 2 squared. Now, whenever you write two square numbers that are taken away from each other, i.e. a square number on the left, a square number on the right, with a minus sign in the middle, that's called a difference of two squares. Now, you can write this as 5 plus 2 times 5 minus 2. And let's see what that would give. Well, the 5 and the 2 would give 7, and the 5 minus a 2 would give 3, and they're being multiplied, and look, you do get the answer 21, which is what we started with. So if you took x squared, well, that is x multiplied by itself. It's a square number. And if you look at the 16 here, that is 4 squared. And there's a minus sign in between them, which means you can write it as x plus 4 times x minus 4. And that's actually the answer. This is how you would factorise x squared minus 16. So if you've got the idea here, you can skip forward, but if you haven't, I'll do a couple more for you. So let's have a look at something like a squared minus 36. Well, how would you factorise that? Well, we've got a squared, which is just a times by itself, a squared, and we've got 36, which is 6 times by itself. So we've written it as a difference of 2 squares. So it means we can write it as a plus 6 times a minus 6. And incidentally, you could have written it as a minus 6 times a plus 6, because they're both the same. Okay? Now, generally, if you want to look at it as just purely algebra, you could have a squared minus b squared. That's the difference of two square numbers, and then you can think to yourself, well, that's just going to be the same as a plus b times a minus b. And you may also ask, why does that work? Well, if you had a plus b times a minus b and you multiplied them out, you would have a squared, which is what you've got here. For this one, you would be multiplying b times negative b, so you would get negative b squared, which is what you've got here. And so you'd be wondering what the other parts of the table would give. Well, you'd have an a times a b, which would be ab, and here you would have a times minus b, or minus b times a, it's the same thing, and you would end up with minus ab. And I hope you understand that a plus ab would cancel with a minus ab, because if you had a positive quantity and you added it to the exact opposite, i.e. the negative quantity, say for example 2 and negative 2, you're always going to get naught. So they would vanish and you'd be left with what you had here. So that's a little bit behind the difference of two squares. So if you see those again, then you can refer back to this and it should help you. Question 29. Solve the simultaneous equations 4x plus y is 25 and x minus 3y is 16. Well, the method that I generally use here is to try and get the numbers in front of the x's or the y's the same. Now what I'm going to write here is 1x, even though you'd never usually write that, and I'm going to write 1y here, so you can see the numbers in front of the x's here are 4 and 1, and 1 and negative 3. Now if I try and get the x's the same for both equations, then what I can do with this equation here is times it all through by 4. And if I did that, I'd end up with 4x minus 12y equals 64. And if I write this equation, which I haven't changed at all, right above it, then that would stay the same. Now, I've got some videos on simultaneous equations, and there's plenty of links to those, which I'll put on here if I can find the time to do so. But with this method, what I'll do is, now I've got the numbers in front of the x the same, I'm going to times one of the equations all the way through by negative 1. It doesn't matter which one at all. I'll choose to do it to the top one. So I'm going to times that by negative 1, this by negative 1, and this by negative 1. And because I've done that to both sides of the equation, i.e. the left-hand side and the right-hand side, then I haven't broken the rules of algebra. And what I always do is I then add the equations together, and here I'd have 0 because I've got minus 4x and 4x, which cancels each other out to give 0. Here I've got minus 13y altogether because I'm adding those together. And if I had a debt of £1 and a debt of £12 and I put those debts together, I'd have a debt of £13. That's a good way of thinking about it. And what do you think I'd have for the right hand side? Well, I have negative 25 and 64. Another way of thinking of that is 64 and negative 25, And another way of thinking about that is just 64 minus 25. So what do you think the answer to that is? Well, it's 39. Now, if you look very carefully here, and we'll write this part out again, we've got minus 13y equals 39. Well, first of all, try and think about the number 13 and the number 39. Hopefully, you can see that 13 does go into 39 3 times, but that's quite difficult, and this is a foundation paper, so I understand that this is rather testing for a lot of students, okay? But if we divided both sides by 13, then what we'd have is minus 1y, or just minus y, is equal to 3. And again, if we times both sides or divided both sides by negative 1, we would have y is negative 3. That's the same as saying minus something is 3, so that something is minus 3. So that's what we've got for a value for y. So we can put that in there. And then with simultaneous equations, if you've got nice values, you can just put them back into the original equations, and it doesn't matter which one you put it into, because simultaneous means that it will hold that value at exactly the same time as the other one. Okay, so let's have a look. Which one would you prefer? Would you rather put y into this one or this one? Well, let's try putting it into the top one. So we'd have 4x plus minus 3 is 25. Well, a positive with a negative in terms of adding and subtracting gives a negative. So we'd have 4x minus 3 equals 25. We could then add 3 to both sides, and we'd have 4x equals 28. And maybe you can spot that 4 sevens are 28 because 4x means 4 times x. So if we divided both sides by 4, we'd have x is 28 divided by 4, which is 7. You could have put it in this one, and that means x minus 3 lots of minus 3, because don't forget that's what y would be. So we got that from the first time we did it. And then notice we've got a negative 3 times a negative 3, which is very similar to one of the questions at the very start of the paper. You may remember we had a question negative 3 all cubed. Well, in this case we'd have x plus 9 equals 16, and I'm sure you can think in your head something plus 9 is 16, that something is 7, and we can just take away 9 from both sides and would get x equals 7. So either way, that would be the answer. Now what I'm urging you to do is to try and look at some of the videos I've done on simultaneous equations, and then if you study those a few times and then come back to questions like this, the penny should start to drop hopefully, and you'll be starting to gain confidence, because these are by far the most difficult questions on this paper.